Welcome. In this section, we'll continue to build upon the guitar distortion electronics that we started in the previous section. So this time we are going to make it using operational amplifiers. So for that I have created a power supply which is plus minus 12 volt, which is generally required by op amps. For the purpose of implementation, I'm going to use a very common operational amplifier called OP07, and I will configure it as an inverting amplifier first and demonstrate it to you. So quickly I'll just put some components around it. I'll be connecting my input to the inverting terminal of the op amp. Let me just wire it. So as you are aware, the gain of this amplifier is actually dependent upon the ratio of resistor R1 and R2. So you can say that gain is equal to minus, because we have connected the input to the negative terminal. This actually is the equation of the gain of this amplifier. So let me just give some values to the resistor. Let's say I'm looking at a gain of 10. So the ratio between R1 and R2 should be then 10. So therefore my R1 will be 100K once I've chosen that my R2 is 10K. And I have to ground my positive terminal of the op amp. So this is a classic inverting amplifier configuration. Also I will connect a signal source to it. Let me just take a signal source. It will be simulating a guitar input. So let's say it's a sine wave of amplitude 1 volt and a frequency 1000 hertz, 1 kilohertz. So this is my sound source, and let me just wire it again. So it will be connected to the ground, and it will be connected to the inverting input of the op amp. Let me name the nets. So let me just call this signal here as in, and this will be the output. Let me call it out. So here we are, and we have to now connect the power supply to this op amp. So if you remember, we had this power supply. Let me just move it closer. Okay, so my positive power supply is power terminal is VCC, so it gets connected to the positive power rail of the op amp. So plus 12 volt to the positive rail, and this is the negative 12 volt, so it goes here. So my op amp is now configured to operate in a inverting amplifier configuration. So let's just test it whether it's working or not. So here the gain is 10, as you can see, 100 divided by 10, so it should be 10, and because there's a minus in front of it, which means the phase of the output will be 180 degree opposite of that of input. So let's just test this first. I'm going to run this. Okay, just a minute, I have not attached this here. All right. So simulation is running here. We have simulated 60 milliseconds of data. Remember, we have this simulation is of 100 milliseconds. So okay, it's done now. So I'm going to connect my probe to the input, and as usual, I'm getting my pure sine wave 1 kilohertz at 1 volt amplitude, plus minus 1 volt amplitude. So this is the voltage in to the amplifier, and now we'll see what's the output. So as you can clearly see that my output firstly is out of phase. So when the input is going through negative phase, my output is going through positive, and when my input is going through positive cycle, my output is going through negative cycle, and it is 10 times the input. So my input was plus minus 1 volt, my output is plus minus 10 volt. So this is working as a typical inverting amplifier. I can actually change this gain. Let me say if it's 30K, then the gain will be 3, and the output will be then swinging between plus 3 and minus 3. So as you can see, this output has now is swinging between plus 3 and minus 3, because my gain now is 3. Here it is. So it's working as an inverting amplifier. And if I take the FFT of this signal, both input and the output, at this point of time, it will not generate any harmonics. The reason is that it's only acting as an amplifier. Whatever is the input, it gets amplified and is being sent as an output. So for example, this is my input and this is my output. And if I take a FFT of this and view the signals in frequency domain, you can see that I generally have V in is red in color, so it's a line spectra at 1 kilohertz, and we have some artifact in the output because of amplifier artifacts, but otherwise it is generating no harmonics here. So now we will do something more interesting and turn this inverting amplifier into a distortion. For that, I will take a diode, as I'm taking the reference of the previous circuit that we had designed, and I'm going to connect it in this configuration as was done in part 1. I'm going to connect it in parallel to the gain stage resistor of the op-amp, that is R1, and I'm going to wire them like this. So there's a very popular diode called 1N914, so I'm going to configure it like that, and this one too. So now I have two diodes, D1 and D2, and they are part number 1N914, very commonly used for switching applications. And let's see what is the impact of connecting these two resistors on this operational amplifier. Let's simulate. It'll take some time. So essentially what you can see is that the moment input crosses plus 0.7 volt, D2, this D2 diode will get forward biased, and a forward biased diode almost acts like a short circuit. So this resistor will become meaningless then, which means R1 will go to 0. And in the negative cycle, when the input is swinging through the negative cycle, when it crosses 0.7 volt, the D1 diode will get forward biased, and then it will act like a short circuit. And since there's a short connected across this gain resistor, this gain, the net resistance across this op-amp in the feedback chain will reduce to 0, and then again the gain is going to become 0. So that's what is my prediction, but let's see what's happening actually. So again, I'm going to connect my probe to the input and then to the output, and something really interesting is happening here. So as predicted, firstly, remember that it's an inverting amplifier, so whenever the input, that is green, is going negative, the output will go positive and vice versa. And the second thing what you're seeing here is very interesting. So as long as the voltage is swinging between plus minus 0.7 volt, which is the biasing voltage for the diodes, these diodes are not conducting at all, as long as the voltage is remaining between plus 0.7 volt and minus 0.7 volt, which means these two diodes are not coming into picture at all. But the moment this voltage crosses plus 0.7 volt or minus 7 volt, this particular resistor, actually the net resistance in this entire circuit becomes 0, because either this diode gets short circuited or the above diode gets forward biased, not short circuited, forward biased. And as a result, you can see this kind of waveform is appearing now. And clearly the output is not a sinusoidal, its rise and fall is very, very steep. In fact, I can make it very steeper because I know that between plus minus 0.7 volt, my amplifier is acting like an inverting amplifier because these two diodes are not coming in picture. So I can give a very high gain. For example, I can make it 100K, and these rise and falling edges will become very steep. So there you are, and now you can see that these rising edge and falling edge has become even steeper. So the steeper it is, the more harmonic component it's going to generate. So let's see the FFT of this. We are going to take both these signals. The red is the input, which is having line spectra at 1 kilohertz, and green is the output, and something really interesting is happening here. You can see that large number of harmonics have got generated, and these harmonics are having enormously high power, almost touching minus 10, minus 20 dB. And interestingly, these harmonics are all odd. So this is the third harmonic. It is happening at 3 kilohertz, then 5 kilohertz, 7 kilohertz, 9 kilohertz, 11 kilohertz, 13 kilohertz, and so on and so forth. So it is generating odd harmonics. Let's see the report. All right. So I hope you're able to see this. So here is my V in, my input, and my input, and these are the number of harmonics here. As mentioned earlier, we are monitoring 20 harmonics. So this is a list of 20 harmonics. And the only significant component in this input FFT is 1 kilohertz, and all other components are quite low. So So the total harmonic distortion is low. So that's as far as input is concerned. But something interesting is happening when we are seeing the output. If you see the output, so expectedly at 1 kilohertz, we have large amount of power, and the second harmonic, which is at 2 kilohertz, is having very low power. It's an even harmonic. Then the third harmonic at 3 kilohertz is having quite a bit of power, though lower than the main component, main frequency, base frequency. Then again, fourth harmonic at 4 kilohertz is having very low power. Fifth harmonic is having very large power, but lower than the first harmonic, and so on and so forth. So you see that odd harmonics are having very large energy components, and there are plenty of them. And as a result, the total harmonic distortion in this output is about 37%. So that's how the guitar distortion is implemented, and I hope you've been able to figure out. Now there are various improvisations that we can do. We can amplify this signal. It's very easy to do actually. We just have to put one more inverting stage in this. So let's quickly do that. If I just take this and connect it like this, and obviously I have to reduce the gain here. It's very high. Let's say it's 60K. So and I'm going to now tap my output from the last stage. So essentially the gain of this stage is 6, and we are going to amplify whatever is the output coming from the distortion or the Clipper circuit. So let's just quickly run this. So here we are. Let me just zoom in. So now you can clearly see that my input is plus minus 1 volt, and after amplification it has become almost 2.5 volt, and again the phase has been restored back to normal. Now the positive cycle of output is coinciding with the positive, is in phase with the positive cycle of the input, and vice versa for the negative. And that has happened because now we have two inverting stages, and so first 180 degree phase shift is coming from here, and the next is coming from the second stage, total 360 degree phase shift, which means 0 degree phase shift. So this is one way of creating the guitar distortion. And let's also just once again have a look at the harmonic components. So they are exactly the same as we discussed earlier. It's just that the signal has now been amplified. So you can see that this is how the guitar distortion is created. The other way of creating it was as shown in the part 1, where we took two diodes and connected them in this manner. So this is another way in which we can create the distortion and then later on amplify it. So hope you have been able to learn something from this. These are the building blocks, and obviously many things can be done after that. You can add active filter stage for the tone control and equalizer part, and you can also insert a circuit for impedance matching, etc. I'm leaving it at that, but many improvisations are possible over this basic circuit. Thank you so much.